We're ready to talk about matter in different terms than we have so far. So we're going to talk about mixtures, we're going to talk about different types of mixtures, and we're going to talk about the physical states that matter can assume, namely solid, liquid, and gas, and some things about what are those? What are the characteristics of solids and liquids and gases at the molecular level? Before we do that, we should do a quick review and talk briefly about what an element, an atom, compound, and molecule are, so we can review what these terms mean. When a chemist says we're talking about an element, these are the varieties of atoms that exist in the universe. So the periodic table lays these out in table form, and one way to think about the periodic table is to liken it to a fruit stand. If you come up to a fruit stand at the farmer's market and there are boxes of different types of fruit there, they're all separated into their own boxes. They might all be types of fruit in the way that all the elements have characteristic types of atoms associated with them, but they have some things in common and they have some things that differentiate one type of element from another. So the elements you can think of as, okay, I've got fruit, I've got apples and oranges, I've got carbon and nitrogen. They're different types of atoms. And the periodic table really lays out all the atoms of which we are aware in the universe currently. This one may not be quite up to date. Chemists are always either synthesizing or potentially discovering the existence of new elements. So, but it's a relatively rare thing. We really know an awful lot about the types of elements that exist in the universe. So an atom is the smallest possible amount of each element that you can have. An atom is a thing. It's like an orange. You can hold an orange in your hand, and if atoms were large enough, you could hold an atom in your hand. And again, the atom might fit into one of those boxes at the fruit stand. It might be a carbon atom, a nitrogen atom, an oxygen atom, ruthenium, iridium, or whatever. But the atoms that we talk about, we almost always use that term in association with an object, a type of, it's something composed of neutrons, protons, and electrons, and it's a thing. When we use the word compound, we're referring to a chemical combination of elements that are assembled in the form of molecules. So if I say water is a compound, what I'm thinking is H2O. This is the formula, and the subscript again represents the idea that two hydrogen atoms are associated with one oxygen atom, and that is true for every single sample of water, regardless of where that sample of water came from, whether it's the water that we know is on Mars or the moon or planet Earth. Water has two hydrogen atoms associated with one oxygen atom. When I use the term compound, I'm usually thinking as a chemist that I've got a collection of molecules of water. For example, chemists might say, what's the compound in that flask? That's water, or that's hydrogen peroxide, or that's acetic acid. Those are all chemical compounds. The atoms in the molecules, we could draw a figure of water here. The atoms are associated with one another through chemical bonds that we often represent as lines like these. But those connections are not by any means permanent. They can be broken, and that's what chemical reactions are. But in many circumstances, we think of them as permanent or semi-permanent. Something like when you have Legos and you assemble something with Legos, you can carry that object around, and the Legos do bond one another tightly enough that you have a semi-permanent structure, but that's the nature of a chemical bond. Different chemical bonds have different strengths, and understanding that is a lot of what chemistry is. So the molecules, analogous to the atoms, are objects, except the molecules are collections of atoms bonded to one another chemically. So let's talk once again about water. I think perhaps if you knew everything there was to know about water, you would know 90% of what we need to know about chemistry. So we come back to model systems in chemistry, look at them through different lenses so that then we can extend that understanding we learn from molecules we begin to know well to those that seem novel to us or perhaps we've never seen. So this model of a water molecule, this model is scaled up by a factor of, I would say, about 1 billion times larger than an actual water molecule. So it's extremely, extremely rare that chemists would study in the lab or manipulate in the lab single molecules. We're almost always working with very large collections of molecules because they're so tiny. It does occur, and it's a very exciting area of research, looking at a single molecule using certain techniques. But generally, we'll be thinking as chemists in terms of water, the compound, and having a collection of the compound. Generally, we'll be thinking about water in these terms. So here I have a graduated cylinder, and it's not quite full of water, but I have perhaps 10 to the 24th power or so within a factor of 2 in this. That's perhaps 10 times more stars than there are in our universe. So if we study water as a compound and we work with convenient quantities like this 100 milliliters in the lab, we're looking at the behavior of many, many, many objects, so many that it's very difficult to comprehend how many or relate to how many water molecules I have in this graduated cylinder. However, because our common everyday experience is with this level of dealing with this compound, this is what our senses allow us to observe. We can smell the water and determine, wait a minute, there's a property about water, it really has no smell. Pure water has no taste. Those are physical properties. So when we study compounds, we have two types of properties that we usually consider: physical and chemical. And most physical properties are related closely to large collections of molecules like I have here. So odor, taste, what are some of the other? Oh, maybe boiling point, freezing point, and malleability, conductivity, and so forth. Those properties almost always relate to how we macroscopically interact with that compound. Chemical properties, they manifest themselves on the macroscopic level, no question about it, but not always. Chemical properties, on the other hand, relate to the bonds that I spoke of earlier. So chemical properties are characteristics of a compound that relate to how easily those bonds break, or perhaps how difficult it is to break them. So chemical properties have to do with chemical reactivity. And reactivity is related to, again, the strengths of the bond. So let's write up a chemical reaction. This is hydrogen gas. The form of hydrogen gas is actually molecular, where two hydrogen atoms are bonded to one another. Two identical atoms of hydrogen are bonded to one another in the form of a hydrogen molecule. And this stuff takes the form of gas, and we're going to talk about what a gas is in a minute. But if you do something to the sample of hydrogen gas, and we'll say we'll add energy for now, you can break the bond, this bond that connects those two hydrogen atoms, and we can obtain two hydrogen atoms. So this coefficient here designates that I started with two hydrogen atoms connected to one another in the form of a hydrogen molecule, and we're going to end the reaction with two hydrogen atoms separated from one another like this. There's no bond between them. This is a chemical reaction, and the reaction arrow designates the conversion of this stuff into this stuff. Chemical reactivity is a reference to a compound's tendency to undergo a certain kind of reaction. And so for each compound, there's a different reactivity. So chemical properties of substances are the tendencies for those substances to undergo react or perhaps not. Coming back to our water sample here, because it contains billions and billions of molecules, those molecules are all contained within this graduated cylinder, and so it doesn't make much sense to diagram only a single molecule. I'll diagram a few up here, and realizing there are billions of these things in this graduated cylinder. When we talk about something like boiling point, we can ask the question on the molecular scale, what happens to water when you boil it, if we're starting with liquid water like I have in here? It turns out these molecules, they interact with one another. There is, in fact, an attractive force between them. We're going to talk a lot about that force as the semester goes on. But the attractive force, it's called cohesive because water molecules stick to one another. So when you see water bead up on a piece of plastic cellophane in your kitchen, if you get a little bit of water on there, you see the beads. That surface tension is caused by the attractive forces between these water molecules. Those forces have to be broken when you boil the water because as the water becomes gas, those molecules are separating from one another. So a physical property like boiling point has nothing to do with a chemical property that we can think of as contained within the molecule. When we boil water and measure its physical property, its boiling point, we aren't breaking any of these bonds between oxygen and hydrogen. However, we are breaking the cohesive interactions between molecules. So liquid water behaves something like you see here. The spheres represent individual water molecules, and you'll notice they're moving, and so they have some what we call thermal energy. There's some movement. And in this water sample, if you take one of the spheres on this side, in a moment or two, you'll find it over here, and vice versa. So they're all moving here back and forth across the bottom of this container, if we imagine this to be a container. So you notice a couple things about the liquid. The molecules are not stuck to one another tightly enough. They stick to one another enough that the water isn't filling the entire volume of this container. The water is remaining at this temperature, room temperature, as a liquid. The cohesive properties of the water are holding the sample of water in the liquid form, and yet the molecules are relatively free to move. So this is how you can swim. You can push molecules aside as you swim. So liquids, while they take the shape of the container that they're poured into, regardless of what the shape is, they don't take the entire volume of the container. That's in contrast to gases. So let's go to a model that represents the behavior of gases at the particulate level. And here that is. And there are a couple things you'll immediately notice. The gas particles occupy the entire volume of this virtual room now. And that's a property of gases. They expand to occupy the entire volume of the container within which they are contained. So the spheres now are bouncing around. You'll notice they travel in what appear to be straight paths until they hit something, either another gas molecule or the walls of the container. So there's lots of space between these gas molecules. And that's why gases are compressible. If you take a balloon and compress it with your hands, you're scooting or squeezing these molecules closer together. You're not squeezing the gas molecules themselves, you're reducing the spaces between the gas molecules. So the macroscopic properties of matter begin to make sense when we think on the molecular and the particulate level. So we've talked about liquids. The molecules are cohesive enough that they bond to one another at the liquid temperature such that the stuff doesn't fly apart and occupy the whole volume of the container. And gases, they aren't bonded to one another tightly enough, and thus they fly apart and occupy the whole volume of the container. Of course, all you have to do with water to assume the gas phase or the gaseous state is to heat it up and boil it. And so that's the boiling point. Again, boiling is a physical thing. Boiling point is a physical property of water, and it's because we're breaking the bonds between molecules, not within molecules, as we are in chemistry. One last state we'll consider is the solid state. And in the solid state, some really amazing things are going on. Now you might guess, well, yeah, I've thrown ice cubes into an empty water glass and see them go to the bottom. They do not. That form of water, that physical form of water, the solid form, does not assume the shape or the volume of the container. So on the particulate level, the reason that is the case is that the water molecules, that the temperature of that sample is so low that the bonds between the molecules that we broke when we boiled the water are so tight that the water molecules are localized to very specific spots in that crystalline form of water, the solid state form of water. So while the molecules might vibrate a little bit in their locations within the crystal, the molecule on the upper left-hand side of the crystal is not anytime soon, or we could really say ever, going to assume the position at the lower right, for example. So the molecules are locked into place. If you look closely at this model of water, you'll see I've colored the bonds connecting hydrogen and oxygen green. I've done that for a very specific reason, to remind you that in our models of molecules, certain features are tied closely to actual properties of the molecule. For example, there are 2 hydrogen atoms for every oxygen atom, but the color of the bond and even the graphic we use to represent the bond is completely arbitrary. Typically, we would color the bonds gray out of habit. Completely arbitrary. These bonds are green because I like green bonds. That's just my thing. So let's zoom in on one water molecule and notice that it is in fact locked into one position in the solid state of water. Water is very unusual because it expands when it freezes. Most substances do not undergo expansion when they freeze. They expand when you heat them up. Later, we'll get to the reasons, well, why is water so unusual in that way? But by studying the solid structure, we can learn why that is. Most forms of matter, most chemicals, are mixed with other chemicals in nature. So, for example, if you go outside and you look around the forest, what you see are mixtures of compounds. You see the living things that are made of mixtures, and if you look at the geology of an area, you see mixtures of chemicals. So chemists are continuously faced with the task of separating the components of mixtures that occur in nature and determining what the chemical components are of those mixtures. So if we consider matter, all of matter, and there's matter, it is composed of 2 generalized types of mixtures, and we call these homogeneous or homogeneous, and heterogeneous or heterogeneous. And homogeneous mixtures are even throughout, and I'll make a homogeneous mixture up here. And heterogeneous mixtures are mixtures that have certain areas of the sample that have a composition that differs from other areas of the sample. So these 2 types of mixtures are very common, and in either case, we use separation methods to pull the components of the mixtures apart and further study them as chemists. So these methods vary from simple filtration to perhaps distillation and even much more technically involved methods. But one of the early steps in chemistry studies and experiments is often to separate mixtures. So for example, if you're a bioprospector and you're in Costa Rica, you identify a plant that native peoples say has a certain medicinal property. As a chemist, you might harvest some of that plant, bring it back to the lab, grind it up and separate out the components, and with the intention of identifying the active, the medicinal compound, so that it can be further studied in a Western medical way than, for example, from the ethnobotany perspective. So this is a big, big part of chemistry, separating mixtures. So let's make some mixtures. I have a beaker here with water in it and some yellow food coloring. So I'm going to drop a little bit of the yellow food coloring in the beaker, and perhaps you can see from there that the food coloring, a couple drops of that food coloring, it's not evenly dispersed around the whole sample. So currently, this mixture is heterogeneous. There are some areas of the beaker that are more yellow and contain more of the dye than others. If I take the stirring rod and stir the sample, what I'm doing is homogenizing the sample. So I now have a homogeneous mixture, and what it is a sample that, regardless of how many samples you take out of the beaker, you will come away with the same ratio or the same composition of the yellow dye in the water. So it's even throughout. It's homogeneous or homogeneous, and we call these homogeneous mixture solutions. So notice this is translucent. It's like Gatorade that you can buy those various and interesting colors at the convenience store, blue, green, and many colors of Gatorade, all chemically based, of course. And so this is something like Gatorade, right? It's translucent. You can see right through it, but it's colored. It's a true solution. The molecules of the yellow dye are intimately interacting with the molecules of the water, and that's what gives this the quality of a solution. In contrast to that example, I have here a can of Spam. Perhaps you're familiar with this meat product. And if I read the ingredients, it seems fairly simple. There's pork with ham, and a few other things, including sodium nitrite and some other things. But this is a mixture of stuff. And in this case, if you open the can of Spam and slice it up, you'll notice there are parts. There are various parts of pigs in each slice of Spam. So it's not just ham, it's pigs in this can. And pigs have lots of different parts. They have cartilaginous parts and they have more meaty parts, and all that's in this can. And so each slice of Spam has a different proportion of this pig and this part of this pig and that part of that pig. And when you look at the slices in the frying pan as they cook, you can see the heterogeneity. This is a heterogeneous mixture. It's one of the reasons Spam can be surprisingly nice to consume. You never know exactly what each slice has in it, so there's that variability that has appeal for some people. Here is a model, a virtual model of heterogeneous mixtures. So you notice the dots of oil, which are, it's a virtual, it's a simulation. The dots of oil have different colors to them, different sizes to them. You notice areas that have no oil and have some sort of other liquid, perhaps water. This is something like oil and vinegar dressing. You know how when you shake the bottle, the things don't mix very well. You've got a heterogeneous mixture. And we understand a lot about why chemicals mix to form homogeneous or homogeneous mixtures and why other chemicals form heterogeneous or heterogeneous mixtures. The particulate level, again, is where we want to be in chemistry. And if we go to the other extreme, if we consider our universe and we look at the number of galaxies and the number of stars in our universe, and if you consider each galaxy, each star is different. The stars that have planets, those planets are different from ours to a certain degree. But billions and billions of stars, there is heterogeneity in these objects. And you can see it by looking at an image like this of our universe. And so from this scale, the largest imaginable, all the way down to the molecular scale, we can make sense and make order of chemistry.